Hello everybody, my name is Abdul Halim Mohamad and my teammate is Mohamad Wad'an. In this thesis project we are going to talk about MATLAB simulating medical fluid pump model with a flow PID controller. In this video we will cover an introduction or a general overview, design and testing, requirements and specifications, test cases and acceptance criteria, results we obtained, and finally a conclusion and future work.
We use an endoscope to examine the interior of an organ or cavity inside the body. Unlike several alternative medical imaging techniques, endoscopes are inserted directly into the organ, providing direct observation. There are three main reasons for carrying out an endoscopy. First, we have investigation to search for the possible causes of symptoms. Second, we have confirmation of diagnosis by taking biopsy samples to confirm a diagnosis of cancer or other disease. And last, we have treatment to treat directly, like sealing an injury or removing a polyp. This project is composed of three main systems of endoscopy, which is insufflator, light source, and we are responsible for the irrigation pump. The endoscopic irrigation system is an important unit of the endoscopy setup. It's the prime instrument that interacts and modifies the operational site as per an operator's need. It is used to clean debris and expand an operating cavity to help the operator's ability to observe, navigate, and diagnose during endoscopic exam, and also monitor and hold the pressure at the operating site to prevent damaged veins from bleeding. It is composed of solution bags, tubes, pump machine itself, pedals.
Based on our previous research, we developed a model for the fluid pump using MATLAB Simulink. MATLAB Simulink is provide an integrated development environment that use building block instead of actual coding. The learning curve is relatively easy for engineers since it shares common mechanisms with other simulation software. And the fact that is developed by MATLAB, the user interface stay coherent and intuitive for the most part. The model is needed to reach an optimal design that can later be translated into a physical device with no need for trial and errors, since all parameters and best part are found using the model. This approach is a new trend in all engineering fields because of the easy and cheap startup of a project. Failures are detected and solved prior to the actual hardware development. This project requires to develop a model for the fluid pump that is close to the one found on the market, with a slight improvement on the flow and pressure control. For that purpose, we use a PID controller to adjust the motor rotation to achieve a quick start and constant delivery of the fluid. What is PID controller? PID controller, which stands for Proportional Integral Derivative Controller, is a control system that uses data from the past and present signal to predict the behavior of a signal and adjust accordingly. Its principle is simple and easy to adjust for any situation where a control system is required, making it the first choice as it is reliable, versatile, and can back up or support a more specific and sophisticated controller. The working principle behind a PID controller is that different weights are applied to an input to correct and obtain the desired behavior of the output. The selection of the right weights is called tuning. Basically, there are three weights: the proportional, integral, and derivative weights are called factors. The input of PID controller is generally the calculated error, which is the difference between the current output and the desired one. The output of the controller corresponds to the adjustments needed to reach the desired behavior of the system. As expected, the PID controller is divided into three controllers with respective weight. P-controller takes the current error value and scales it, so its information is only dependent on the present value. I-controller integrates the error over a period of time, so it uses the past information from the system. D-controller, its output is the weight multiplied by the rate of change of error with respect to time. The derivative controller anticipates the behavior of a signal in the next iteration, so the D controller is related to the future state of the signal. In our case, the PID controller controls the motor rotation speed to reach the desired flow of fluid. The result is that the desired flow is reached quickly, with little to no overshoot, and kept constant regardless of the increasing pressure. That is supposed to decrease the flow, but with the help of the controller, the motor speed is increased to adjust to the needed force to overcome the pressure inside the operation site.
The model is composed of two main paths. The electromechanical path is responsible to provide the adequate force to move the fluid inside the fluid path that goes from fluid bags to the operation site. The fluid hydraulic path follows the flow of the fluid from the tank representing the fluid bags to the accumulator representing the operation site. This part of the model is not included inside the actual machine. The tank serves as the fluid bag. It is kept at a constant height to provide a basic flow due to gravity pull. The pipeline serves as the tubing set that feeds the fluid from the bag to the pump and then to the operation site. The spring-loaded accumulator serves as the actual bladder. It has a maximum capacity same as the bladder and provides a pressure that is proportional to the volume.
In a physical machine, the electromechanical path is located inside the machine. Its main component is the DC motor with its controller circuit. For simplification purpose, some of the small and non-critical components are not represented in this video, since they don't directly affect the outcome of the design. The main components are PID controller. For the flow control, it takes a feedback from the flow sensor and controls the motor speed to achieve a constant speed. Next, we have the speed and current control for the DC motor. Used to control the DC motor, the controller uses a feedback system based on a Hall effect to reach and keep the desired motor speed. Then we have the DC motor driver. Amplifies the current received from the motor controller into the appropriate electrical current for the DC motor to move it at a desired speed and direction. Next, we have the main mechanical components, the DC motor. It provides the given torque that moves the fluid. It's a brushed DC motor with a maximum speed of 3,500 revolutions per minute. After the motor, we have a gearbox. It's the interface between motor and pump head to help provide a higher torque. Finally, we have a fixed displacement pump to serve as the peristaltic pump head. It is the interface between the mechanical part with the fluid hydraulic part of the system. It squeezes the tube, so moving the fluid at a given flow proportional to the rotational speed. Based on the developed model, we can design a physical device. The following block diagram represents a possible configuration. The hardware may differ from the model because some components are added for safety and monitoring, such as power switch and power supply, a touch screen interface, and a proximity sensor to sense if the tube is inserted. Note that the PID controller is included programmatically on the control board. Our model is designed to work on the bladder, so we selected the following specifications. Maximum pressure 50 mm mercury. Maximum volume 1.6 liters. The main parameters to track for a safety and efficient work are the flow and the pressure. A high pressure can damage the operation site, so we need to monitor it and keep it under the critical pressure. Whereas the flow affects the speed and efficiency of the pump. A weak flow extends the operation time, and it's if not efficient at moving waste or debris. For the testing, we turn on the pump and let it pump the fluid to the operation site with a constant flow and turn off the pump when the maximum pressure is reached. To ensure the efficiency of our model, we graph the following parameters to make sure they behave as expected: the flow result, pressure result, volume result, and revolution per minute result. As we see here, on the left side, the figure denotes the response of flow PID controller with weights set using Simulink auto-tuning tool. It shows some high-frequency oscillations, meaning the system is not stable, even though by averaging it shows a constant flow. Thus, oscillation means the motor is turning on and off really fast, which is the physical problem and can damage the hardware and cause higher electrical power usage. And on the right side, the figure shows the response of a flow PID controller after manually setting the weights. It shows a better result. The system reaches the desired flow in a matter of seconds with little overshoot and keep the flow constant until the motor is turned off.
This figure shows the variation of pressure with time. As expected, it increases as more volume is pumped. The maximum pressure the bladder can hold is 50 millimeter mercury. So the system was designed to stop the procedure when that pressure is reached. The spike at the end is due to the model used for the bladder. It stops the volume abruptly, causing an increase of pressure at the outlet.
As expected with a constant flow, the volume of fluid in the feeding bag decreases at a constant speed, as we see in the figure. It stops at 0.4 liters, meaning that a total of 1.6 liters was delivered, which is the maximum capacity of model bladder.
This figure shows the speed of the motor in rounds per minute. Note that this is the output of the flow PID controller. The spike at the beginning is the result of the system trying to reach the desired flow at the quickest time. Also note that the RPM increases slightly with time. This is to overcome the increasing pressure at the outlet, which is due to the increase of fluid volume in the model bladder.
In silico or computer modeling plays a major place in the advance of technology. It shortens the workflow and development time by predicting errors and malfunctions prior to the actual manufacturing, saving both time and money, unlike the deprecated traditional way that relies on trial and error. Our model for the fluid pump is stable and performs well, and can be used as a core design by biomedical device manufacturers to construct their new devices. The model can also be used by regulation agency like the FDA to make sure that a device is safe prior to insert it on the market. And finally, it can be used for teaching purpose since it includes multiple fields of physics like electronic, mechanical, and hydraulics. Throughout this project, we gained a lot of knowledge, starting from the biomedical device market, how they are organized, from hospital to private providers when we were doing a review of the device on the market. We also gained technical experiences when we investigated the pump Ingenious Medical provided for us. We experienced firsthand how biomedical engineers predict and find solutions to possible errors and keep the device safe for both patient and the operator. Finally, we grew as engineers in research and development field by designing a model from scratch and experimenting to optimize it and making it safe and reliable. Our model is performing well within the set criteria, and we try to keep it as generic as possible so that future work can be done to build a specific design for a specific device for a specific field. But it is far from complete. More work can be done, like changing the PID controller into more sophisticated controller, like an MPC controller that can track multiple input for the regulation of the flow. Also, a more accurate model of the bladder should be added to replicate the physiological response of a pressure change to help tune the model to make it more reliable. The testing procedure can be enhanced to include noises and errors to see how the system reacts and adjust to adapt to the situation and keep the patient safe in any case. Finally, thanks for your listening.